Okay, so we're continuing on, and we are talking. We talked about Markov chains, and now we're going to talk Markov chain Monte Carlo, right? And all of this stuff, this Monte Carlo, this whole course, the big theme is math can be hard, and because math can be hard, we're going to have the computer do stuff to get an idea of what we want to look at, okay? And so Markov chain Monte Carlo, this is, it's just another way to generate a big sample from some distribution that we want to understand, okay? So this is another, it's like, is this all we're gonna do in this class? Kind of. This is like Monte Carlo stuff, right? So this is another method to generate a sample from some distribution that is, and then in parentheses, that is too hard for us to figure out analytically, right? And I know some of you are wondering, I'm struggling with these Monte Carlo methods. I think it's easier just to draw directly from the theoretic distribution. Yeah, you know, for some, I know in our homework example, like for the adaptive rejective sampling, the target distribution is the chi-squared distribution, okay? And we understand the chi-squared distribution. It's easy for us to draw directly from that. We don't need adaptive rejection sampling. But that's just an example. You might have some crazier distribution that's harder for us to understand. When we have a unidimensional, so far we've only been dealing with one dimension, okay? And when you're dealing with one dimension, it's actually really easy to kind of do these like non-Monte Carlo methods, but we can, you know, approximate integrals easily for one dimension because, you know, if you have an interval, you just say like, oh, I want 1,000 values on this interval, and you can space it out very easily with one dimension. And that would be called a, you know, a grid method. And, you know, it's very, very easy, very powerful, and it works great if you've got one dimension. As soon as you start climbing dimensions, though, like if you have 2 dimensions, instead of 1,000 grid points between, you know, on your x, now you have x1 1,000 and x2 another 1,000. So now you have 1,000,000 grid points to evaluate. Okay, and then if you had 3 dimensions, now you have 1,000,000,000 grid points. And so as the number of dimensions increase, the grid approximation starts to break down. Okay, so, you know, maybe I don't know. Are you guys familiar with this idea of grid approximation? It's pretty much all that we've been doing, not all that we've been doing, but a lot of times when you create a graph of a function in R, you're doing grid approximation because generally when you create a plot, you've got some kind of function, right? You've got f is some function of x, okay, and you plug in the value of x. And we don't ask R, plot the function directly. What do? We say, oftentimes we'll say x is a sequence from, you know, I don't know, 0 to 10, and we say phi is equal to 0.01 or something. And so now x has length, what? 1001 or something like that. Okay, and then we say, what do? We plot x versus f of x, and we say type is equal to L. Right, this is often like if we want to plot a curve in R, this is probably how we do it, right? And then, and so basically what R is doing is it's calculating 1,000 different dots here, 1,000 different dots, and then it connects them all, okay? And because the 1,000 dots are so close together, to us it looks like, oh, it's a nice smooth line or something, okay? It's a nice line, but it's not. We're not actually plotting the function itself. We're plotting a grid approximation where we have 1,001 grid values, okay? And when you have one dimension, sure, 1,000 values, that's not too bad, okay? With one dimension, you only have, with one dimension, you got, 1,000 values on the grid, okay? On the grid, that's easy, okay? 2 dimensions, now you have 1,000,000, right? Now you have, if we had a function of 2 dimensions and we wanted to do grid approximation, you'd have, x1 and x2, and then you have 1,000 values here, and then 1,000 values here, and then we would get some kind of surface, right? And maybe that's a little bit more complicated. Now we have a million values to calculate. Million grid points. Okay. When, I don't know how familiar you guys are with Bayesian stuff, okay? With Bayesian stuff, and maybe we'll talk about all of this Markov chain, Monte Carlo stuff, and then we'll come back and we'll talk about Bayesian stuff and do an example where like all of this slogging through that we've been working on, maybe we'll do an application and see like, oh, this is where it's actually useful. So if you're doing Bayesian stuff with one dimension, you can just do grid approximation, and it's easy. You just say, oh, okay, well, we've got my likelihood function. I'm going to calculate 1,000 values on the likelihood function. I got my prior function. I'm going to calculate 1,000 values for my prior function. And even evaluating the marginal distribution for a Bayesian thing, if you've got one dimension, it's not too bad. You just evaluate the 1,000 points. You sum them up to get an approximation of the integral, and now you got it, okay? But again, when we have grid approximation, this works well with one dimension, but as soon as you start climbing the dimensions, you've got too many grid points to figure out, okay? So, but in higher dimensions, this doesn't work. Okay, so Monte Carlo, Markov chain Monte Carlo, this is a way for us to generate samples from some distribution, even a high dimensional distribution, without having to do grid approximation, without having to figure out the math. We just say, I'm going to start off with this little algorithm rule, and then we're just going to see where it goes. And we just keep track of where we end up, and this works as a kind of a random sample drawn from the distribution. Okay, so MCMC, we just, we start somewhere. This is like the most colloquial explanation. Okay, so we start somewhere, and then we follow the rules, okay, and keep track of where we go. And then if we do this right, after we've kept track of where we've gone, we have a pretty good approximation of the distribution. Okay, if we let this run long enough, okay, all of the locations we've been will resemble the target distribution. Okay, so we're going to start off with something. This is like the most basic. I don't know about most basic, but it's like the first Markov chain Monte Carlo algorithm that we learn, and it's called the Metropolis algorithm. The Metropolis algorithm. Okay, and so before I actually get into how the Metropolis algorithm works, we're going to illustrate it, and I'm going to use, I really like this book. I'm going to use the example coming from the textbook, okay? And the example, this is an illustrative example. All right, and so the idea here is there's some island nation or island, and it consists of a string of islands, okay? Okay, so it's an island. And we have a politician who wants to visit each of the islands, okay? And I don't know, do campaigns or whatever it is, okay? Politician wants to visit the islands, wants to visit each island for, you know, campaigning. And the politician wants to visit the island in proportion to the population on the island, okay? So we go, so, you know, the island with the highest population, the politician wants to visit the most. The island with the smallest population, the politician wants to visit the least, okay? So, you know, we want to visit the islands in proportion to the population. Okay, and this is, you know, analogies, they always kind of break down a little bit, and this is where the analogy says, well, this doesn't quite make sense. All right, we're going to say we don't know the population of each island, okay? We don't know, at this point, we don't know the population of all of the islands, okay? So the actual distribution of population, that is unknown to us, okay? Of the population among islands is unknown. Okay, but what we can do is, given if we are on a certain island, okay, let's say we label these 1, 2, 3, you know, 4, 5, 6, 7. If we're on this island here, what we can do is we can call, I don't know, the mayor of the island, and we can get the population of this island. We can get the population of the neighboring island and the two neighboring islands, okay? We can get the population of the current island and the population of the neighboring islands. All right. And you might say, well, if we can do that, why don't we just call all the islands and get the all the populations, figure out the distribution? But we're going to say, okay, but that's all we can do, and I don't know, for whatever reason we can't, I don't know, figure out the entire population of the entire island chain. Okay, this is the part where it doesn't make sense. But we're going to say all we can do is we just know the population of the place we are now, and we can get the population of the kind of the two neighboring islands. And then as the politician goes and travels, the politician has options. Okay, either the politician will stay put at the current island, or and do like another campaign or whatever, another rally, or the politician goes to the island to the right or the east and the island to the west. Okay, so we have three options for travel. Okay, stay put, go to the east, we'll just say right, or go left, west. Okay, go east, which is to the right, or go west, which will be to the left. Okay, and so this is going to be the Metropolis algorithm. The Metropolis algorithm is the rules we're going to use to decide whether we stay put, whether we go to the east or go to the west. So this is how we do it. Okay, what we do is we're going to start off and we're going to find the island. Well, okay, no, first we flip a coin to say, should we consider going left or right? Okay, so we just flip a fair coin. Okay, and we'll say heads. Oh, it doesn't matter. Okay, flip a fair coin to decide whether to go left or right. To go, east or west. Okay, so that happens with 50% probability. Okay, and here's the key part. We call up, we find the current population, and then we find the population of the proposed island. Okay, and if the proposed island has a population that's bigger than the current island, we will go to the proposed island. Okay. If the proposed island has a smaller population, then we have to we make a decision. We basically do kind of like an accept reject thing. Okay, if it has a smaller population, we find the ratio, kind of proposed population divided by current population, and then we pick a random uniform, and if it's smaller than this number, we'll go, and if not, we stay put. Okay, we find this ratio, so this will be called, we'll call this probability of move, and we move with this probability. We go to the proposed island with this probability. So what that looks like is, draw, one value from random uniform, and if we'll say u is less than p move, then move. Okay, otherwise remain. Okay, does this kind of make sense? So we start at a certain island, we flip a coin, and this says, do we propose going this way, or do we propose going this way? Okay, and then if we propose, once we have a direction proposed, we say, okay, how big's your island? How big's our island? Okay, if that island is bigger, we definitely want to go there, right? We want to visit the big islands more, right? Okay, and so if it's bigger, we go there. If it's smaller, okay, we still want to visit the small islands, but not as much, but less often. So if the island has a smaller population, then we come up with this ratio, proposed versus current, and then we go based on with that probability. Okay, so if the proposed island has a population that's 3/4 of the current population, then we go with probability 0.75. Okay. All right. So let's try this out. Okay. And so we're gonna so in our example, we're gonna pretend that there are 7 islands. So we'll pretend we have 7 islands, and we index the islands with theta. Okay, so we've got 1, 2, so we have theta 1, 2, 3, 4, 5, 6, and 7. Okay. And we will, we'll look at the and then we'll say the size of the islands. We'll just say the populations of the islands are directly proportional to their index, just to keep it simple. Okay, so the politician doesn't know this, but we will say, the population is basically equal to theta, times a constant. So maybe we multiply it by 1,000. Okay, so island 7 has a population of 7,000. Island 2 has a population of 2,000, and island 1 has a population of 1,000. Okay, just for simplicity, we will do this so we can kind of get an idea of how big the islands are. Okay, so population of each island is equal or is proportional to theta. Okay, so the population of the island is proportional to theta. So this will keep our calculations of whether or not to move simple. All right. Okay, so let's say we start at time 0. We will start at 4. Okay. So we'll say or is it time 1? At time equals 1. At t equals 1, we'll say theta equals 4. Okay, so our politician is right here. And then we'll flip a coin. And in this case, the coin says go to the right. Okay, so when we look at island 5 is bigger than island 4, so we go there. Okay, coin says go right. Island 5 is bigger than island 4, the population, so we go to island 5. So this is now time t equals 2. Our theta is equal to 5. Okay. All right. The next day, we flip the coin again. Okay. Okay, and now this coin says go left. Okay, so we look at island 4, and so now the probability of moving is going to be equal to basically the population of 4 divided by the population of island 5. Okay, and we said the populations are proportional to the number, so the probability of moving is going to be 4 divided by 5. We have a 0.8 chance of moving to the left. Okay, and we will say, you know, we generate u, and it happens to be over 0.8. Okay, so we generate a u. Generate u, and u ends up being 0.8. So we remain put. We stay on island 5. Okay, so at time t equals 3, we are still at island 5. This is okay? All right, and then we just try this again, okay? And then let's say, so we flip the coin again. So you know, flip a coin again, and we'll say coin says left. And so now probability of moving again is going to be 4 over 5, 0.8, and then this time we move. And so at time t equals 4, we are now at theta equals 4. Okay. Again, I guess we would generate u, you know, and then this time u is less than 0.8, so we move. Is that okay? All right, and so this is just one possible sequence of events if we started off at 0.4 and we just kind of ran through the algorithm. Okay. Let me just kind of show you what could happen with the with the random walk. Okay. Let me actually, the pictures here will be a better example. Let me see if I can find this. Okay, so in the beginning, we will say we start off. This is kind of the probability. So we will start at theta equals to 4. Okay, and so at time 1, we have a probability of 100% or 1 of being at location 4. Okay, and then let's think about the probability of ending up at 5 and ending up at 3 and ending up at 4 at time 2. Okay, so at time 2, at t equals 2, right, we flip a coin. What's the probability we will end up at 5? Okay, if the coin says go to the right, we're definitely going to end up at 0.5, right? So, or at island 5. Okay, so the probability of being at 5 is equal to 0.5 because that's, you know, the coin says right. Okay, and on the other hand, if the coin says left, then there's two possibilities. We can either remain or we can go to 3. All right, and so we will remain with, we will go to 3 with probability 3/4, right? So we're going to have 0.5 times 3 over 4, and so we can end up at location 3 with probability 0.375. And we can remain with probability 1/4, okay, given that it says left. And so we will remain with probability 0.125, right? Are these kind of calculations okay? So here I'm just applying the kind of our transition probabilities to our current location of 5. I mean, location of 4. Okay, and so that is displayed in this graph right here. So at time 2, this is where we could end up. We can end up at location 3 with probability 0.375. We can end up at location 4 with probability 0.125, and location 5 with probability 0.5. Okay, and then now what do we do for time 3? At time t equals 3, okay, so now we have a bunch of things to add together, right? We can end up at theta equals 6, okay, so the probability of going to 6, well, we're currently at, that means from 5, the only way to get to 6 is we are currently at 5, and we multiply, and the coin flip tells us to go to the right, yeah? So this is going to be 0.5 times 0.5, and we get a probability of 0.25. Yeah? Okay. What are the ways we could end up at location 5? So now there are 2 ways to end up at 5, right? We can start at 5 and stay put, or start at 4 and go right. Yeah? Okay, so we start at 5 with probability 0.5, and we will stay put if the coin flips to the left, and we move with probability 4 out of 5, and we stay put with probability 1 out of 5. Is that okay? So this is probability of start at 5. This is probability of coin says left, and this is probability of stay put given coin says left. So actually all of these have givens, right? Given ... and given ... So that's one of them. And then we have to add, starting at 4, we start at 4 with probability 0.125, and then we move to the right with probability 0.5. Yeah, so you have to do all of this calculation. This is a pain in the butt. And then we get the probability of getting to location 5. And then we can figure out for 4 and figure out for 3. And so after you do all of those multiplications, this is what you end up getting. So we can see that the height at 6 is equal to 0.25, and then the height at 5, I mean, I guess I could do these calculations just to kind of make sure that we have this. What is this? 0.5 times 0.5, 0.25 times 0.2 is 0.05 plus 0.12 plus 0.0625. So 0.05 plus 0.0625. This gives me 0.1125. Okay, and that looks correct there. Okay, so this is 0.1125, and then this one has probability 0.25. Okay, and then we could do it for 4, 3, and 2, and we would get some number, and this is what we have. Okay, and after but even at time equals 3, there's no way we could be at island 7 or island 1. Yes, question. This is the probability of staying put, right? So if we start off, we're talking about how do we end up at location 5. We end up at location 5 if we start off at 5, we flip the coin, it says go left, but we decide to stay put, right? Because when it says go left, the neighboring island has a smaller probability, or a smaller population, so we're only going to go there with probability 4 out of 5. which means we have a probability of 1 out of 5 of staying put. Yeah. That's so this is from the previous point in time. From the previous point in time, we had a probability of 0.5 of being at location 5, and you know, probability of 0.125 of being at location 4, and probability of 0.375 of being at location 3. So we're starting off here. We apply basically our transition rules. Either we go to the right with this probability, or we go to the left with this probability, or we stay put with this probability. And then after applying the transition rules to kind of these starting probabilities, this is what we end up having. This is okay. So these are the probabilities. Given that we've started at location 4, after 2 iterations of applying our Markov chain rules, this is the probabilities of where we're going to end up after just 2 iterations. Okay. After the 3rd iteration of time t at time t equals 4, this is what we end up looking like. Okay. And so we can keep applying the rules and say, like, okay, well, this is where we'll end up at time 5, 6, 7, 8, you know, 9, 10, 11, 12, so on and so forth. After 12 iterations, the resulting probability of being at island 7, island 6, 5, 4, 3, 2, 1, this looks very similar to the actual target distribution, which is proportional to the islands, right? 1, 2, 3, 4, 5, 6, 7. So this is the target distribution that we're looking at. And so if we keep applying our transition rules, saying if I start here and I'm going to go to this island with this probability, or go to the other island with this probability, transition from one state to another state, we can see that if we let the Markov chain run long enough, the probabilities of where I end up landing looks very much like the target distribution. Okay, so you know, it might not be so clear that this simple rule for the Metropolis algorithm will give us these results. Okay, and I'm not going to try to have you guys prove that the Metropolis algorithm gets us there, but this is just an illustration of if I start here and I apply kind of my transition rules, and that at the next time I'm going to have these probabilities of ending up here. If I apply the transition rules again to this thing, at the next time I have this probability here. And when we use these transition rules, this Metropolis algorithm, what ends up happening is that the stationary distribution, meaning where we end up after applying, you know, all of these transition rules over and over and over again, that stationary distribution will look like the target distribution. Okay, and so we'll, yes.
Why the probability of we start at 5 equals 0.5?
So this is just, you know, I just said let's start at 4, okay? At time 1. At time 1 we start at 4. So we have 100% or 1 probability of 1 of being at 4, okay? So then at time 2 I can end up at location 5 with probability 0.5, because if I flip the coin and it tells me go to the right, I'm going to go to the right because island 5 has a bigger population than island 4, so I definitely go there. Okay, so that means I have a probability of 0.5 of ending up at island 5 at time 2. I'm using this as a starting point for my probabilities for time 3. And so I say, okay, I'm going to start off with these probabilities, right? So we're looking at kind of the previous step, or saying at the end of time 2, I had a 0.5 probability of being at island 5, 0.125 of being island 4, and 0.375 of being at island 3. Okay, and so now I apply the rules, and I say, okay, I have a 0.5 probability of starting at 0.5, which means I could end up at island 6 if, if I flip the coin and it tells me go to the right again, okay? And if it tells me to go to the right, then I go to island 6, okay? And thus the resulting probability of being at island 6 at time 3 is going to be 0.5 times 0.5, because I had a 0.5 probability of starting at island 4, and so to be at island 6, it's going to be that. And then the probability of being at 0.5 is going to be a combination of starting at 5 and remaining at 5, and starting at 4 and going to the right. And so, we do that calculation. This is starting at 5 and remaining at 5, which means I had to start at 5, I had to flip a coin that says go left, and then after it says go left, then I draw my probability and I end up staying put and that happens only with probability 0.2. And then the other one is I started at 4 and I ended up going to the right, which is going to be 0.125 times 0.5. Okay? And that's just for 2 of these, and then we could do the calculations for all of the other ones. It's kind of tedious, but with a computer and figuring this out, we can do it easily, right? If you had to, I think this would be a reasonable question to put on like an exam form where I say, you start here, these are the rules for moving, can you tell me the probabilities that you'd end up at these things after 2 iterations, right? So it's just applying the rules for the transitions after 2 iterations, and it's I think it's a very you'll have to do all of these calculations, but it's a straightforward, and I think you'll get a clear picture of how the transition matrix is being applied to these states here. Okay, we'll end here. We're going to keep talking about the Metropolis algorithm on Friday, okay? And then you got Data Fest on Friday, so we'll talk this and we'll keep going. So.